And
Yeah. Good evening, all. I hope all of you fine.
good evening, sir. Fine, sir.
Yeah, let's start the class.
Yes, sir.
Right. Just a minute, I want to make it happen. Today we are going to discuss about the photochemistry of alkenes and dienes.
2:30.
Yeah. Here we are two types of unsaturated compounds are there. These are simple alkenes. These are also known as olefins. They are having double bonds. Double bond. And this dienes, these are alpha beta unsaturated or conjugated double bonds. Then, when we are irradiating these compounds with light, then what's happening? Generally, these kind of compounds are participating in the following reactions. One is my voice is audible to you?
Yes, sir.
Yeah, right.
Yes, sir.
One cistrons isomerization. Cistrons isomerization of when you take a double bond. A specific double bond we consider in a molecule, then on the specific double bond, this kind of isomerization reaction that takes place. And the second, acyclic addition to alkenes. In previous case, cyclic additions we are seeing. After addition, a cyclic products or the cyclic products are dissociated to and two different products are generated. But here acyclic product. After addition reaction, there is no cyclic product formation. The such kind of reactions are known as acyclic additions of alkenes. In previous case, we've seen that two olefins are combined together, undergoes the addition reaction that leads to the formation of a cyclic product. Okay, such kind of reactions are get seen. These are called cycloaddition reactions. But other than this cycloaddition reaction, we're going to understand the next type is acyclic addition reaction of alkenes. Next, specifically, we are studied about the dienes, that is the photochemistry of dienes, that is the photoisomerization, photodimerization, right, of conjugated double bonds, photochemistry of conjugated dienes. Next one is a very important reaction, that is isolated double bonds are involved in the reaction. Such kind of isolated double bonds are gives a specific product. Such kind it is the name reaction, very important reaction. It is called diphine methane rearrangement reaction. In this chapter, the most important topic is this one. Diphine methane rearrangement reaction generally appear in the short answer questions. Generally, it is appear in the short answer questions. Right. Next one. After methane rearrangement, the fifth kind of reactions are intermolecular cross addition reaction. Intermolecular, intramolecular, intramolecular cross addition reaction. Intramolecular cross addition reaction. The sixth one, oxidations using singlet oxygen. Oxidation of double bonds or saturated bonds using singlet oxygen. Oxidation using singlet oxygen. Singlet oxygen. In that, you see in that in reactions, these are also important in the when we are considering the exams. In reactions and dioxetane formation, dioxetane formation, and third one, dioxane formation. Actually, when you are learn all these things, we can combine both thermal synthesis and photochemical synthesis. We can discover new molecules. Okay, but the scope of research is very high once you are understanding all these photochemical reactions. Some of the some part of the product is prepared with the thermal reaction. Some part is prepared with the but just a minute. Next, oxidation with superoxides. Oxidation with superoxides. These are the general reaction we see when you are studying of the photochemistry of alkenes and aldehydes. Now, first coming to the important reaction, cis-trans isomerization of alkenes. Cis-trans isomerization of alkenes. Cis-trans isomerization of alkenes. Cis-trans isomerization of alkenes. Right. Then, first I'm going to give you the one example. Then I will discuss about the things what's happening during the cis-trans isomerization. Right. Here I am considering a steel molecule. This is the simple double bond. This is substituted with at the two carbons of the two hydrogens and at the two carbons with the two phenyl groups. Right. This is called as cis Tilbene. Name is Tilbene. Then it's geometrical isomer. What is that? It's geometrical isomer. Next one, that is trans. Just consider the trans arrangement of the product is like this. This is the trans Tilbene. Trans Tilbene. Right. Now, but if you take cis-Tilbene or if you take trans-Tilbene, right, it is irradiated with light. Sorry, light. It is irradiated with light. Then products are, suppose the trans is isomerized to cis product. Cis is isomerized to trans product. Right? These are the isomerization reactions. The cis will be converting into trans. The trans will be converting into cis. Right? Therefore, it leads to the formation of, even it is the cis Tilbene is undergoing the isomerization reaction that leads to the formation of cis Tilbene along with trans Tilbene. The two products will be appear, a mixture of products will appear. In that mixture, the major product is the cis product, whether you take the trans isomer or cis isomer, the product ratio is like this. The 7% is the trans, 93% is the cis Tilbene, just 7% is the trans. What's happening? What's happening in this reaction? Then, before going to discussing about the mechanism of that reaction, then this is the thing happening when the cis-trans isomerization of olefins or cis-trans isomerization of alkenes. That means one isomer is converting into another its corresponding geometrical isomer. That is called cis-trans isomerization. In this cis-trans isomerization, 5 to 5 star singlet state of non-conjugated olefin and 5 to 5 star triplet state of conjugated olefin are undergoing in the reaction. Again, I am repeating, 5 to 5 star state of non-conjugated olefin, or even though it is the conjugated olefin, first it generates the 5 to 5 star singlet state. If you take a simple double bond, simple ethylene, if you take a simple ethylene, all the substitutions are hydrogens. This is called ethylene. right? Or it may be a conjugated. Look at here. This is the phenyl ring. All the double bonds are in conjugation. This double bond is also in conjugation with these three triple bonds present in the phenyl ring. Similarly, this is also phenyl. Three triple bonds are double bonds are in conjugation. These conjugate double bonds are also conjugated with the double bond. Now this is called as conjugated olefin. This conjugated olefin, non-conjugated olefin. If anything is happening involving in the reaction, that first it is generating 5 to 5 star singlet state. 5 to 5 star singlet state. And it requires for generating 5 to 5 star singlet state, 5 to 5 star singlet state, it needs it needs 180 to 200 nanometers, actually 210 nanometers for the non-conjugated olefins and sorry, non-conjugated olefins. If it is conjugated olefin, it requires the starting radiation is 220 nanometers. Then what is the conjugated olefins? These are the conjugated. If we are using conjugated olefins, we need to irradiate the starting material to minimum 220 nanometers of wavelength of the light. That means for this photochemical radiation should be 220 nanometers. Then only it generates the first initially generates the 5 to 5 star. When you are using the simple olefin, that is non-conjugated olefin, we need to radiate the starting material at 180 to 210 nanometers. At that at that condition, it generates the N2 5 star singlet state. Then this N2 5 star, sorry, 5 to 5 star is converting into 5 to 5 star triplet state. 5 to 5 star triplet state. How it is possible? That is the intersystem crossing by the triplet energy transfer. By the triplet energy transfer. That is the formation of once it forms the singlet state, that singlet state is converting into triplet state. For this interconversion is called intersystem crossing. In that intersystem crossing, a triplet energy transfer will be takes place. Right. This triplet 5 to 5 star is involved in the reaction. If 5 to 5 star triplet state is involved in the reaction. Now, in the cis-trans isomerization of olefin takes place under photochemical condition in two major conditions. The starting materials which are used in the reaction, that is especially in the cis-trans isomerization reaction, that one is a liquid state. The reaction is carried out at a liquid state. And the second one, vapor phase. Vapor state. The liquid state means it is existing in the reaction part as a liquid. Vapor state means that whatever the starting material you are using in that reaction should be in the gaseous state. Vapor state means gaseous state. Then what's happening in the liquid state? What's happening in the vapor state? Once you take the liquid state, once you observe the or you are taking the starting material in the liquid state, where the side reaction dominate, where the this cis-trans isomerization reaction takes place very predominantly, right? Predominantly, cis-trans isomerization is taking place. Cis-trans isomerization is takes place. Is that visible to my screen? Is my screen is visible to you? Suppose if the reaction is carried out in vapor state, instead of cis-trans isomerization, a side reactions are takes place. Side reactions or takes place. Okay, that is the difference between the reaction conditions. When you are conducting the reaction under liquid state, you will get the cis-trans isomerization reaction, cis-trans isomerization reaction, or if it is you are conducting in the vapor state, that will be leads to the formation of side reaction that leads to the decreasing the cis-trans isomerization products, decreasing the percentage of cis-trans isomerization products. Therefore, when you are conducting the vapor state reaction, other than cis-trans isomer, other products may be generated in the reaction. The reaction. Okay, this is the best example we can explain. Best example, this reaction is carried out in the vapor state that leads to the undergoing the cis-trans isomerization. Then it leads to the formation of 93% of cis-stilbene and a 7% of trans-stilbene. Even we are conducting the reaction with the cis-stilbene, the same ratio of products will be generated, or trans-stilbene is also produced the same amount of mixture is generated in the reaction. Now coming to the mechanism is also very important to understand the, how this trans isomerization is takes place. Then you coming to the mechanism, take the mechanism. Just a minute. Just a minute. Okay. Coming to the mechanism of the reaction. To explain the mechanism of reaction, I am considering both isomers are involved in the reaction individually. Okay. Now this is the carbon, the still being double double CC double bond. Now it is attached with the phenyl ring. It is, I think, just imagining that it is a flat molecule. When while you are observing the molecule, while you are observing the molecule, the hydrogens are near to you. Phenyl group is far away, right? Right. Now there is a other bond is there in between the carbon and carbon. That is the pi bond. That pi bond is the double bond in that is generated by the overlapping or sidewise overlapping of this pi bond. Sorry, p orbitals. Sidewise overlapping of this p orbitals. Right. Now the pi bond is the overlapping of this. The pi bond is generated by the overlapping of this unhybridized p orbitals. Now when you are irradiated this, when you are irradiated this cis still beam. This is a cis still beam. Cis still beam. I'm irradiating the light, right? Irradiating the starting material with light. Then first it is undergoing pi to pi star transition state. Transition. During this transition, during this transition, that leads to the generation of first pi to pi star singlet state. Pi to pi star singlet state. After first generation of that singlet state, then in the second one, it is undergoing intersystem crossing. IC, ISC, intersystem crossing. That means triplet energy transfer. Triplet energy transfer. Once the triplet energy transfer, that leads to the formation of a transition state. The transition state is the pi to pi star triplet state. Pi to pi star triplet state. Pi to pi star transition state. Triplet transition. Once you see this, once you see this, in the singlet state, both the electrons in the transition state are opposite spin. But whenever it is converting into a triplet star, triplet transition state, it is a pi to pi star triplet state. In that, the both the electrons which are present on the double bond of the pi electrons are parallel spin. These are the parallel spin. This kind of transition state will not undergo any reaction. But for, for, for the sake of reaction, it need to undergo a CC bond rotation. Need to undergo CC bond rotation. Then on, when it is undergoing CC bond rotation, this electron, any one of the electron, it undergoes spin inversion. It undergoes spin inversion. That spin inversion leads to the formation of or initiate the new new bond between these two filaments. This, first, it is undergoing a relaxation. What is happen when it is undergoing relaxation? The triplet energy excited state undergoes the relaxation. That means the triplet energy is converting into its corresponding singlet state. How it is relaxing? By it is undergoing the CC bond rotation up to 90 degrees. This bond rotation, bond rotation of CC bond, bond rotation of CC bond. In the CC bond rotation, you keep the carbon, one of the carbon is at constant position. It is undergoing 90 degrees rotation. Look at here, there is no change in the position of this unhybridized p orbitals arrangement. But whenever it is rotating 90 degrees, you are rotating 90 degrees, how it is appearing? Just like it is appearing like this. I will show you how it is. Just a minute. This time I will show you in the 3D part, 3D model. That's why I'm just right. Are you seeing this one? Two orbitals are appearing to you. Now I am rotating the cadence. In this particular not undergoing any rotation. Rotate. Suppose if it is rotating 180 degrees like this, right? It is the sidewise viewing actually. Once this is suppose the double bond is like this. So the 3D model is not working. Okay. Look at it. These two are perpendicular to each other. Once you are rotating it, this is in the fixed position. You are rotating the CC bond. This is the actual 90 degrees. Once you rotate it, it will be 0 degrees. It will be 0 degrees. Now you are watching the molecule. You are watching the molecule from this direction. From this direction. How it is appearing? Suppose this is the straight horizontal line. The orbital is like this, right? Whenever you are watching the molecule, it will be appear like this. It will be appearing a circle. A circle-like appearance will be appear. That means you can only see one lobe. This lobe can be appear whenever you are watching from this direction. It will be hide from the. It will be hide the block shaded or the positive shaded one will be hide. Therefore, once you are rotating 90 degrees rotation, it will be appear like this. It will be appear like this. It will be appear like this. That means this is not a circle. It will be lobe. That lobe. It is another lobe is there that will be hidden from this. Right. Now the two electrons. How these two electrons are arranged? One of the electron is like this, and another one electron is like this. Right. When you compare here and here, that geometrically perpendicular to each other. Geometrically perpendicular to each other. Now this is called as common triplet intermediate. Common triplet intermediate. Common triplet intermediate. Okay, how it is common triplet? We are seeing just still B. Now you are going to see that. Now you are going to see that A trans Stilbene. If I am considering the trans Stilbene. How the trans Stilbene is there? I'm keeping constant from at this position. Means here the two phenyl rings are arranged in the opposite direction. Two phenyl rings are arranged in the opposite direction. Look at here. This is the trans Stilbene. Trans Stilbene. Now, whenever you are irradiation with light, again it is also undergoing 5 to 5 star transition, 5 to 5 star transition, and second one it is undergoing intersystem crossing. That is the triplet energy transfer. Now it leads to the formation of a triplet energy transition state, that is the 5 to 5 star, 5 to 5 star triplet energy state, 5 to 5 star triplet energy state. The arrangement is like this. Page. Now, at this state, both the electrons are, we take, sorry, the 5 to 5 star triplets. Look at here, both are similar. For generating the next intermediate, it needs to undergo relaxation. The relaxation means higher energy state to lower energy state, and it is undergoing bond rotation. The second step is bond rotation to disappearing the triplet state energy. That is bond rotation to get stabilization. Bond rotation of CC bond that leads to the formation of the same intermediate. You kept constant. It is undergoing the 90 degrees rotation. Then, whenever you are watching this orbital, you can see only one lobe. The backside lobe will be hidden. Therefore, it is appearing like a circle. Now, both will give the same. Both of them are giving the same transition state. Both of them will give the same transition state. Right. Now, this same transition state, either it is undergoing to complete rotation, then it leads to the cis isomer from the trans isomer from the cis, or it is the cis isomer from the trans. Right. Therefore, it leads to the formation of the two products. That is, this intermediate is undergoing decay. That leads to the formation of cis stilbene, and a trans stilbene and a trans stilbene. Okay, look at here. Whenever you are understanding the mechanism, whether it is undergoing the reaction cis-stilbene or a trans-stilbene, the intermediate generated by the both the isomers are same. Due to that reason, it leads to the formation of two isomers, but with different ratios. This is about the 93%. This is about 7%. Okay. Now, whatever the common triplet state is there, a common triplet intermediate is obtained. That is known as that is known as perpendicular triplet state. Perpendicular triplet state. This is called perpendicular, or a also called as phantom triplet state. That is called PTS shortcut. PTS or twist triplet state. This is called twisted triplet state. Twisted triplet state. Right. Then this twisted triplet state or phantom triplet state or perpendicular triplet state undergoing the non-radiative decay. This decay is called non-radiative. Non-radiative decay that leads to formation of 93% of the cis isomer and 7% of the trans isomer. Okay. Now, when you're coming to the energy discussion, if the object is to prepare a perpendicular geometrical isomer, the choice of wavelength is the more important to decide. Choice of the transition state, choice of the wavelength, whatever the wavelength of light you are using for the state, that is important. Using radiation of wavelength where the more stable isomer absorbs more strongly than the less stable isomer. I'm again repeating. Using radiation of wavelength where more stable isomer can absorb more strongly than the less stable isomer. Therefore, the first one. Predominantly is the cis isomer for the above example. Right. In particular, in the steel beam case, 330 nanometers gives the photostationary state. That is whatever the transition state we are discussing. Photostationary transition state. That is the equilibrium mixture. That is about 93% of cis steel beam and 7% of trans steel beam will be generated. Okay. That is called photostationary state. That is called photostationary state. Right. If you see the other examples, we have the several examples that are there for this reaction. For example, you can take the cis steel beam with a different radiation. In previous case, the cis steel beam may be irradiated with the 190. I've already given 180 to 210 nanometers, and the trans steel beam may be at 220. That leads to the formation of same interval. But here, when the steel beam is irradiated at 330 nanometer, it gives the photostationary state that containing 93% of steel beam and 7% is the trans steel beam. Right. That means the same product, same kind of product will be generated. Only the trans steel beam can give the 7% whenever we are a specific ratio, specifically we are irradiated this steel beam at 330 nanometers. At the photostationary state, it gives the trans steel beam. This is the trans steel beam that is consisting only 7%. The remaining that 93% in the react is the cis steel beam in the reaction mixture. Similarly, if you take a cyclohexadiene, cyclooctadiene, cyclooctadiene, which is on irradiation with light at 280 nanometer, 280 nanometers, 280 nanometers. After the formation of photostationary phase, look at here, the trans isomers will be like this of the cycle product. The trans isomer of the product that is the trans isomer. Is the double bond? Is the also double. Here, this double bond will undergo the isomerization that leads to the formation of trans isomer. That is up to 37% at the photostationary phase and 63% is the other. Right. Similarly, if you take Other reactions. We have several examples are there. In the several examples, you can read and understand. Okay, the formation of these products is always depends on the energy of the both the isomers which are involved in the reaction. Suppose if you are using a triplet sensitizers like triplet sensitizer like esters and carbonyl compounds and xanthones, thioxanthones or benzene or toluene kind of sensitizers are used in that sensitized isomerization with the energy of triplet state of sensitizer will be in between the two isomers. The isomer with lower energy will be sensitized and the photostationary state will be reached with the isomer of the higher energy triplet state. In the photosensitization of an alkene with a negligible intersystem efficiency, crossing efficiency, always the olefin it is not a conjugated one. Therefore, it leads to the formation of pi to pi star singlet state. That the generated pi to pi star singlet state is converting into twisted singlet state. Twisted singlet state. Later, it is undergoing the CC bond rotation. Then it leads to the formation of double bond. After formation of the double bond, it leads to the formation of that corresponding other isomer. Suppose CC is undergoing the reaction, that leads to the formation of a pi to pi star singlet state. After formation of the pi to pi star singlet state, it is undergoing twisting. That is the twisted singlet state of the transition state will be generated. The twisted singlet transition state is undergoing the rotation. Then it leads to the formation of bond under it is undergoing the non-radiative decaying. Then after the non-radiative decaying, it leads to the formation of a double bond product. Then it leads to the formation of trans. That is called cis-trans isomerization when the only olefin which is not a conjugated. So for example, I am going to a generalized olefin, a butane, sorry, butene to butene. It is a cis isomer. It is a cis isomer. And in presence of bromine, you know that at the room temperature when you are adding the bromine, it is undergoing oxidation. But we are irradiated with a specific wavelength of light that leads to the isomerization, that leads to the isomerization. Then it will form a here horizontal three product will be generated. Okay. The halogen atom, if you are adding to the olefin, first it is generating the radical. Then further it is undergoing the elimination of the halogen atom from the radical yields. Radical it yields a mixture of cis transition. The mechanism, when you are observing the mechanism, that means bromine and bromine, and you are irradiated light, that leads to the formation of the bromine radicals. These bromine radicals will react with the that olefin. Only double bond is there without any conjugation. Then this bromine is interacting with olefin that leads to the formation of the bromine is attracted one plus that radically it is interacted with one carbon. Then at the other center it generates the radical. At other center it is generating the radical. Now this radical is influences the behavior of CC single bond nature. Now the CC single bond may undergoes the rotation more preferably 90 degrees that leads to the formation of isomerization. Then it leads to the formation of both the products cis and trans isomers. Cis and trans isomers. And this the ratios of these products always depends on the wavelength, the energy of wavelength which is involved in that reaction, which is involved in the light. The wavelength of light we are applied on the reaction that will be influenced in that percentage of the products. Okay, this is called as cis-trans isomerization of olefins. Next, coming to the second reaction, acyclic additions. Acyclic additions. Acyclic addition reaction. Acyclic addition of alkenes. Right. In general, when the photo addition of water, suppose some substances, whenever we are irradiating with the light, the water is undergoing the addition reaction with that particular substrate. For example, you take methanol. Here, a small molecule like water, alcohol is also a neutral molecule like water. When you compare the water and alcohol is slightly acidic, but water is a neutral, right? When in presence of alcohol and the xylene solution, xylene solvent, we are irradiated the reaction, then it is undergoing simple addition of the alcohol molecule at the double bond that leads to the formation of product. Sometimes it may lead to the exocyclic double bond. How it is generated? In presence of sensitizer, you are irradiated light. Then it leads the first it generates the 5 to 5 star, 5 to 5 star singlet state. The 5 to 5 star singlet state, the energy will be transferred from this sensitizer. It leads to the formation of 5 to 5 star triplet state transition state. It leads to the 5 to 5 star triplet state transition state. Is 5 to 5 star transition. This 5 to 5 star transition state in the presence of methanol, it undergoes the protonation. Undergoes protonation. Then it leads to the formation of a cation type intermediate. A cation type intermediate can be isolated. Then it is further undergoing the another molecule of alcohol and the oxygen, alcoholic oxygen, they have lone pair that will be donated that leads to the formation of this product, right? Sometimes it may lose the proton. It may lose the proton. It leads to the formation of, not from here. It loses the proton from the this position, ethyl group, losing the proton. Then it leads to the formation of this product. So this is the mechanism. Then what's happening? Alcohols and carboxylic acid, water, alcohol, carboxylic acid are undergoing photoaddition with carbon-carbon double bond have been reported in several studies. Cyclohexane and cycloheptene, which cannot undergo cis-trans isomerization due to the small ring size, but undergoes and photoaddition reaction with alcohols and carboxylic acids and water. In these additions, 5 to 5 star triplet state is the transition state which is obtained from the photosensitization. That olefin, that 5 to 5 star triplet state olefin is undergoing protonation even in the weak acids like water, alcohol, the carboxylic acid. Sometimes a trace mineral acid may also will influence this reaction to produce this kind of products. If you are assuming that carbonium ion is the intermediate is supported by the observation of rearrangement, whatever the rearranged product is generated. This is the main evidence for the formation of carbocation. The carbocation is generated. It is further undergoing the addition with the Methanol that leads to the formation of which fully saturated cycloalkane derivative. The formation of this carbocation intermediate or carbonium ion intermediate is confirmed by the formation of this product. How it is generated? Just a simple elimination of the proton from the methyl group that leads to the formation of this kind of exocyclic double bond compound. Right? That is the only evidence is clearly indicates that the carbocation generation of the reaction. Generation of the reaction. We have several examples are there, we can see. Okay. The same reaction if you are carried out in the carboxylic acids, what's happening? Suppose the same reaction, one methyl cyclohexene is treated with acetic acid that leads to the formation of this reaction is again plasma of light and orthoxylene. Then it leads to the formation of acylated product is generated. But acyl here the acetic acid addition is takes place. Acetic acid addition is taken. Similarly, we can choose two or three reactions are there in your group. You can use it. Okay. Next kind of reaction is photochemistry of conjugated dyes. Photochemistry of photochemistry of conjugated dyes. Photochemistry of conjugated dyes. First, you need to know what are the conjugated dyes. This is 1,3 butadiene. 1,3 butadiene. Suppose if it is undergoing the trans isomerization, this is the trans butadiene. Actually, this is called S cis 1,3 butadiene. S trans. Here the S represents the sigma bond. Sigma trans butadiene. Butadiene. Okay, such kind of molecules are known as conjugated dyes. You can see also these are also coming 1 comma 3 comma 5 hexatriene. Comma 3 comma 5 hexatriene. Similarly, if you go extended like this is the 1, 2, 3, 4, 5, 6, 7, 8. Okay, suppose 2, 3, 4, 5, 6, 7, 8, 9. 1 comma 3 comma selenium 1, 3, 9 carbon. 1, 3, 5 tetra how many carbon? Octatetraene. Octatetraene. So such kind of molecules are known as octatetraene. All these kind of molecules are known as conjugated dyes, right?
Sir, sorry, sir.
Uh,
1357, sir.
yes, yes.
One three.
1357. Sorry, the 7 is missing, right? 1357 octatetraene, right? Uh, can you excuse me if your power is off? I think my laptop is out of power. Right. I will continue in tomorrow class. Okay.
Okay, sir. Okay. Thank
Okay.
you.
Thank you.
Okay, sir. Thank you.